So let's continue with our wave solutions, shallow water equations and equatorial waves. I'm not always remembering to turn on this laser pointer, but hopefully the cursor can be seen anyways. Okay, so we used these vertical mode structural functions in the meridional direction, and we wrote this function, plugged it back into the governing equations, and produced this what is basically a Schrodinger equation for a simple harmonic oscillator, which also includes this constant. And to satisfy the side boundaries, you need certain conditions like the equation here. So solutions to this equation that decay away from the equator are well known, from which it follows that constant part of the coefficient in the parenthesis must satisfy this relation, square root g he, which is the gravity wave speed, beta is the Coriolis gradient, df dy, omega is the frequency, he is of course the equivalent depth, which is just essentially a parameter, as I said before, k is the zonal wave number, and n equals 0, 1, 2, so on are here the meridional modes or the nodes. Yes, okay, the number of nodes. I don't know why I got stumped there. Okay, so let's just jump to solutions, but I should make a point here. If you know there is a w squared here and a w here, that's a cubic equation which should have 3 solutions, but n equals 0 and n equal minus 1 offer 2 more solutions for Rossby wave and Kelvin wave, so we end up with 5 outcomes, wave forms coming out of this equation that we derived from the shallow water set of equations, the Laplace tide equations that we called, which we transformed into the harmonic oscillator equation. So the solutions here: dispersion curves for equatorial waves up to n equal 4. As a function of the non-dimensional frequency, it's very common to do non-dimensional transformations as well, and non-dimensional zonal wave number k star, where omega star is converted from omega using this transformation, omega divided by the square root of beta times square root ghe, and k star is transformed using k times square root ghe divided by beta to the 1/2. For all but the Kelvin wave, these dispersion curves are solutions to equation 6, which is this one. So the Kelvin wave has to be extracted by putting n equal minus 1 for consistency with that equation. Westward propagating waves relative to the base 0 basic state. We have actually already discussed Doppler shift, the importance of the background circulation, zonal shear, zonal variability of the winds, the westerly duct, and so on and so forth. When we derive the free waves, typically we are deriving it on a 0 basic state. They appear on the left here. Eastward propagating waves appear on the right. So the k star here is negative and positive, and omega star is positive. As I said before, there is a convention used where omega is also allowed to go negative, but let's not worry about it now. For consistency with equation 6, the Kelvin wave solution is labeled n equals minus 1. So there is your gravity wave, which has a constant omega over k and d omega dk. The group velocity is the same, so when you have phase velocity and group velocity to be the same, you have energy and waveforms propagating in the same direction. The n equals 0 solution, which is also special, provides us the mixed Rossby gravity wave, so it can behave like the gravity wave on this side and asymptotically behaves like the Kelvin wave or a gravity wave on this side. And the Rossby waves 1 to 4, you can see the lower wave numbers or longer waves have a d omega dk that is negative, so westward propagation, and they have transition to positive the omega decay here, so the shorter waves can propagate eastward. So that's something to remember. Again, we are doing this as a very short introduction, but you can look up my tropical dynamics course if you want to go through all the details of deriving the equations and going through these details of these spectrum wave number frequency spectral diagrams. So here we have again n equal 1, 2, 3, 4 for the westward inertial gravity waves and eastward inertial gravity waves. So again, the slope has to be looked at for determining the direction of the phase speed. Okay, so this is the set of equatorial waves, and we obviously can look at their characteristics. The numbers here 18, 19, 20 is just in the paper, and I didn't take the time to edit it out. So here we are. Important characteristics of the wave solutions are as follows. Since original shallow water equations were linearized, any linear combination of the wave solution is also a solution. Right? The phase speed of the Kelvin wave, a non-dispersive wave, is c equals square root GHE, where HE is the equivalent height. The phase speeds of all types of inertial gravity waves, either eastward or westward, asymptotically approach the magnitude of this for large k. So you can see as k star increases, they all head towards this line of the Kelvin wave. Okay. The equatorial Rossby radius of deformation, which governs the rate of decay of solutions with distance away from the equator, is given by Re equals square root GHE over beta to the 1/2, so square root of this whole thing, and has been used to scale horizontal lengths in figure 3. We already saw how omega went to omega star and k went to k star. In practice, Re is on the order of 10 to the 0 of latitude for CCWs, so 1 times the latitude, which means the Rossby radius of deformation increases with latitude for convectively coupled equatorial waves. You have to develop some intuitive sense for Rossby radius of deformation. In a rotating system, it's how far, let's say, a wave can travel before it begins to feel rotation. So you can see there's a gravity wave speed and the rotational effect beta. It's also done, I mean, there are many ways to think about it, so let's not worry about it. You just remember this much. The horizontal energy dispersion of waves is governed by the group velocity CGX, group velocity d omega dk, which you know, which may be estimated from figure 2. So you just take the derivative. The mixed Rossby gravity wave, for example, has westward phase propagation. Omega over k is negative everywhere, but eastward energy dispersion. Okay, so that's something to remember. The inertial gravity, so it depends on which way the energy is going, depending on the wave number, whether it's in the same direction as the phase speed or in the opposite direction, right? So inertial gravity and Kelvin waves tend to be more divergent in character, whereas mixed Rossby gravity waves and equatorial Rossby waves are more rotational. Okay, so divergence versus rotation. Just remember these features. The shallow water depth HE determines the speed and scale of the waves, and for the purpose of modeling motions of the full atmosphere is called the equivalent depth. In the context of real atmosphere, however, in no way should the equivalent depth be thought of as a physical depth, but as an important parameter of the theory. We will see this later on. So when you have a fully stratified system and you derive waves out of this, you have to project them onto these equivalent depths, which is basically a parameter to match, let's say, observations to the theoretical calculations. Okay, so I hope I have I don't know, somehow I have an empty slide there. So let's look at quickly at the structures, the horizontal structures of, so let's just go here. These is showing n equals 0, k star equal -1, so it's a mixed Rossby gravity wave, and n equals 0, k star equal 1, eastward inertiogravity wave. Remember, we have eastward and westward inertiogravity waves. The divergence and convergence are shown in these shades. So this is convergence, this is divergence, and these are geopotential heights. So when you are in a particular hemisphere, obviously you can relate the anticyclones and cyclones to the changes in the geopotential heights, but the waves, mixed Rossby gravity wave has off-equatorial maxima in convergence and divergence and geopotential heights, and has this antisymmetric structure, so low and high, high and low kind of structure. And the eastward inertiogravity waves also have similar asymmetric structure. This is for n equals 0 mode. So you can see, again, these are the number of nodes you have in the meridional direction, 0 crossings, if you will. So obviously, when you have cross-equatorial flows, it's not so easy to relate geopotential heights to the circulation, but when you are within the hemisphere, you expect that the anticyclone and divergence versus cyclone and convergence are going to affect the atmospheric column by stretching or compressing it, so the geopotential heights correspond to those. And when we look at the equatorial Rossby wave, it has maxima off the equator, symmetric for the k star for n equal 1, and again you have convergence and divergence, or divergence here, convergence there, and you have the anticyclone, cyclone associated with this on either side. This is what we meant by Kelvin waves and inertial gravity waves being more convergent, divergent, whereas Rossby waves being more rotational. Okay, so here you see again convergence, divergence for the Kelvin wave here, with V is essentially 0, and there are details of how geostrophic balance works in these, and how the amplitude maximum for the Kelvin wave is always on the equator. Of course, there are coastal Kelvin waves as well, especially in the ocean, that we're not going to worry about. We'll just worry about the equatorial waves here. So you have high geopotential, low geopotential, so cyclonic, anticyclonic, but you have to be careful which hemisphere you are in. So boom, boom, convergence here and divergence there.